Inshallah, today I will be talking about a new topic, which is isentropic efficiency. Isentropic efficiency is a parameter that is used to evaluate the performance of steady flow devices involving turbine, compressor, and also nozzle. We evaluate the performance of those devices adiabatic system under the adiabatic condition using what we call the isentropic efficiency. The isentropic efficiency is the ratio, as the name indicates, is the ratio between the actual work divided by the isentropic work. Isentropic means we don't have losses, so that should give us indication about the performance of such a system. And it is limited, ya shabab, to the turbine, to the steady flow devices, adiabatic systems, turbine, compressor, and nozzle in this case. Right, let's look at this isentropic efficiency and see how we can define this isentropic efficiency for those steady flow devices. We said we have turbine, and also this parameter is applied to the case of compressor. All steady flow adiabatic systems. So the systems are adiabatic. Okay. So if we have a turbine, compressor, and nozzle, how we can evaluate the isentropic efficiency of this system? But let's start first of all with turbine, in case when we have a turbine. But let's consider a steady flow turbine here. So the process through the turbine is an expansion process in which actually the flow is coming at high pressure, as you know, and high temperature like steam or something. Then it is expanding inside this turbine from a high pressure to a low pressure. So the pressure V2 should be less than V1, and the temperature is expanded. And due to this expansion, actually we can generate shaft power out of this turbine. Okay, so this is the turbine. Right. Let's study this turbine like what we have learned in chapter 5, draw a control volume, and look at actually masses coming in and energies coming, and then we can apply the first law of thermodynamics in this case to calculate the shaft power. We have gone actually through all of this process. If you apply the first law of thermodynamics, Q dot minus work dot will equal to M dot multiplied by delta H, neglecting kinetic and potential energy, then it will be only delta H. You don't have a change in kinetic or potential. If this turbine is adiabatic, so that means heat transfer is zero. So this term in this case is equal to zero. If I divide the whole equation by M dot, then in this case we can get the specific work out of this turbine should equal to, we have here negative sign, delta H, H2 minus H1. Then the work, we can take the negative sign to the other side, it will equal to H1 minus the difference in enthalpy. And we said this earlier, we said if we represent this process on the Molière diagram, which is the HS diagram, the process through the turbine is expansion. So this is the line of pressure B1, and this is pressure B2. B1 is at the inlet, and B2 actually is the outlet pressure in this case. Okay. So if the flow is coming here at high pressure to the turbine, if this process is going isentropically mean actually the entropy S1 is the same as S2. Isentropic mean we don't have a change actually in the entropy, and in this case delta S should equal to zero, and we don't have any losses within this system in this case. And the exit point of this turbine, I will call it 2S. So S1 is the same as 2S if the process of expansion inside this turbine is an isentropic process. But if the process is isentropic, so delta S is zero. We said the entropy or the change of entropy give us indication about what? Entropy. If we have a system and the entropy is increasing, so delta S is giving us indication about what in this system? About the losses within this system, exactly. So if we have an isentropic process, that means the process is reversible and adiabatic, so we don't have any kind of losses. So in this case, delta S is equal to zero, and we don't have losses within this system. But delta S give indication about the losses. What about delta H here? Delta H here give us indication about what? About the work. So the difference H1 minus H2 based on the energy equation give me indication about the work of this turbine. But this work is which work? From 1 to 2S. This is the process is isentropic. So this delta H give me indication about actually the isentropic work or the reversible work for this turbine which is called also as the maximum work of this turbine, because we don't have any kind of losses if the process is isentropic process from point 1 to point 2s. But in case of actual turbine, the process actually should have some losses, and these losses will be converted to entropy generation, and the entropy generation will result actually in a change or rise of the entropy. So usually the expansion process inside the turbine result actually in entropy change, in this case delta S, due to the irreversibilities within the system. And based on this, actually this expansion should leave at point, let's say 2A in this case. Type the difference H1 minus H2A. It should be less than the difference H1 minus H2S, because in the actual case we have some losses. So that means actually delta H, which is H1 minus H2 actual, should give me indication about the actual work inside this turbine. And the isentropic efficiency of the turbine is the ratio actually between the actual work divided by the isentropic work. And the actual work, if we consider based on the energy equation, work actual should equal to H1 minus H2 actual, the actual exit point. This is the actual exit point, okay? Type if it is isentropic, so the work isentropic will equal to the same H1 minus H2S in this case. 2S, which is the isentropic exit condition in this case, if the entropy S1 is the same as S2. And in this case, we can define the isentropic efficiency of the turbine as H1 minus H2 actual divided by H1 minus H2S in this case. Okay, so the isentropic efficiency شباب of a turbine is the ratio between the actual work divided by the isentropic work. Actual specific work, which is the difference H1 minus H2 actual, and isentropic work, which is the difference between H1 minus H2S. H2S is actually the condition at which the flow is leaving at the same entropy as the end station. Okay, is that clear, شباب?
Yes, so it depends on the exit only.
Yes, but for both cases, شباب, how we link point 1 and 2S? S1 is the same as S2S, which is the entropy is constant. Okay, so in case of process from 1 to 2, S1 is the same as S2S. So what about point 2S and point 2 actual? They should have been at the same what? At the same pressure in this case. So B2 actual for the actual exit point, it is in the same pressure line like the isentropic exit point. So in your exam or any problem, it will just give you the exit pressure. This exit pressure can work for the 2 points, the actual and the isentropic point in this case. Okay? So let's solve an example here. He said we have a steam, enter an adiabatic steam turbine. So the working fluid is steam. We have to record this. And the device is a steam turbine. So I have to recall chapter 5, apply the first law of thermodynamics, and this will be the sequence in your exam. Just I will give you, it is typically a problem like what we have learned in chapter 5, but what is added here, he will just, in this case, he will just ask you to calculate the isentropic efficiency. So in this case, we have a steam turbine, steam, he said the steam, enter an adiabatic steam turbine, so the working fluid is steam, and the device actually in this case is a turbine. He said adiabatic steam turbine, so the heat transfer is equal to 0 in this case. He said the pressure at the inlet, so the pressure V1 is equal to 3 megapascal, and the temperature T1 is equal to 400 degrees C. So the steam is coming into the turbine. So here is the turbine. Steam is coming actually at point 1 at this given pressure and the given temperature. He said steam actually is leaving this turbine at pressure B2, that B2 actual, and it is the same as B2 isentropic. It is the same pressure. If the process is actual or isentropic, it should be the same pressure. He will not tell you, Shabab, this is the actual exit condition or the reversible. Okay, he will just give you the exit pressure and exit temperature, and by default, this exit pressure and exit is the actual value. Pressure is the same for actual and isentropic, but actually temperature is not the same. So the given temperature is T2 actual, which is equal to 100 degrees. Okay, So B2 actual is the same as B2 isentropic, but actually they should not have the same temperature because they have actually different enthalpy. Okay, so temperature, given temperature in this case شباب is the actual value. He said the power output of this turbine, the shaft power output of this turbine is equal to 2 megawatt in this case. And we need to calculate the isentropic efficiency of this turbine, and also we need to calculate the mass flow rate of steam, M dot steam in this case. So how we can proceed, Shabab? So if the isentropic efficiency is required, then I have to start my solution with the isentropic efficiency, the definition of the isentropic efficiency, which is H1 minus H2 actual divided by H1 minus H2s. So this is isentropic efficiency, which is H1 minus H2 actual divided by H1 minus H2s. But how we can get H1, H2 actual and H2s? So the working fluid is steam. So at pressure P1 and temperature T1, usually the pressure of steam and the condition of steam at the inlet of a steam turbine is superheated. It should be superheated. But in your exam, you have to check this pressure and temperature. Go to table A5 with the pressure, get the saturation temperature, compare it with the given temperature. You will find that the temperature is greater than the saturation. Then I will be using table A6 to calculate the value of the enthalpy H1. I can get the value also of the entropy S1 because it is needed. S2S is the same as S1. I need to get the value of S1 in this case. Okay, so here at this pressure and temperature, I can get this value of H1 and S1. But what about the actual point, the actual two actual? In this case, we have the pressure is given and also the temperature is given. For the inlet condition, you don't need to check because you are sure steam coming into a steam turbine should be superheated. You can just double check, as I said, if you want. But for the exit point, you have to check. Okay, because we don't know is it superheated or it is saturated mixture in this case. So with this pressure, 50 kilopascal, I will go to table A5, get the saturation temperature, compare it with this given value. You will find also that the temperature T2 actual is greater than the saturation temperature. So still the state is superheated. I will be going to table A6. Then I will calculate, I will get the value, not calculate. Get the value for H2 actual at this given pressure and given temperature. But what about the process for the isentropic process from 1 to 2s? How we can calculate H2s? We have B2s as the isentropic exit condition is the same as B2 actual, 50 kilopascal. What is the other property? Entropy, exactly. We have S2S as the isentropic exit condition is the same as S1. And the S1, I got it actually at the inlet condition. Now I have pressure and one specific product. With this pressure, I have to go to table A5. What I should do, I will get what? S fluid, and also I will get S gas. Compare them with the given value here, entropy, which is the same as S1. You will find the entropy S2S for point isentropic exit point is greater than S fluid and less than S gas, so the state is saturated mixture. So in this case, if it is saturated mixture, I have to calculate the quality of this case, X2S, which will equal to S2S minus S fluid divided by SFG. You can get the value of SFG directly from the table, or you can take the difference S gas minus S fluid. But I need to calculate H2S, not actually the entropy. So in this case, from the table at this pressure also, I can get actually the enthalpy H fluid, and also I can get HFG directly, not H gas. Then we can say H2S as the isentropic exit condition would equal to H fluid plus X2S, which we just calculated, multiplied by HFG. Then we can calculate the enthalpy of the isentropic exit condition H2S. Now we have, this is the definition. Now we have H1, H2 actual, H1 and we have H2S, then we can calculate the isentropic efficiency of this turbine. If you calculate this value, it will equal 2.667, or about, actually multiplied by 100, it will be about 66.7%. And this is the isentropic efficiency of a turbine. And usually the isentropic efficiency is even higher. It can approach actually 90%. Okay. Because usually gas turbines are adiabatic, so don't have heat loss. So most of the input heat actually is converted to work with at minimum losses. Okay. But we need to calculate as well the mass flow rate of steam. Okay. This is based on what we have learned on this chapter today, the isentropic efficiency of a turbine. Now we have a turbine and we need to calculate mass flow rate of steam. It gives us the power. We're going to apply the first law of thermodynamics as you used to, Q dot minus work dot equal to M dot multiplied by H2 actual minus H1. He said this is the first law, neglecting kinetic and the potential energy, like what we have learned in chapter 5. This is the adiabatic system, so the heat transfer is 0, so the actual work will equal to M dot multiplied by H1 minus H2 actual, because we have negative sign here. Okay. طيب, the power output of the shaft power output, which is given, is it the actual or the isentropic?
Actual.
Should be the actual. Any given value, that is the actual value. Actually, the isentropic conditions, those are actually imaginary conditions, or a conditions that cannot come to reality. He cannot tell you actually this turbine gave you this power and this is the reversible power. No, he should give you the actual value. So the actual work which is given is equal to 2 megawatt. Let's convert it to kilowatt multiplied by 10 to the power 3. That equal to the mass flow rate, which is mass flow rate of steam, multiplied by H1 minus H2 actually. This is in kilojoule per kilogram. This is in kilowatt. It should be like this. Okay, you should not leave it in megawatt. It should be kilowatt because this is in kilojoule per kilogram, and that should be actually in kilogram per second. Okay, so we have the actual work is given H1 and H2 actuals, and we can calculate the mass flow rate of steam. Mass flow rate of steam here is equal to 3.64 kilogram per second. Okay, is that clear, Shabab?
Yes, clear.
So, the problem is typically like what we have learned in chapter 5, but what has been added here is just the isentropic efficiency of the turbine. We have learned that the isentropic efficiency is the ratio between actual work divided by the isentropic work, or difference in enthalpy at inlet minus actual enthalpy at outlet divided by H1 minus H2S, which is H2S is the isentropic exit condition. We just call the isentropic exit point as 2S. And this 2, we can leave it as 2 without any suffix description, or we can just say 2 actually, and just to indicate the difference. Okay, but this is the case when we have a turbine. This is how we can define the isentropic efficiency. Let's move to a compressor. If we have a compressor, how we define the isentropic efficiency of the compressor as a steady flow device, steady flow adiabatic device. We said anyway, the isentropic efficiency should give us the ratio between the actual and the isentropic work. But this is in case for the work producing devices like turbine. Turbine is producing work. So if it is reversible, we don't have losses, this work should be maximum. Is it?
Yes.
If it is, yes, it is. If the device is producing work and we don't have any losses, by default, this work should be maximum. But what about if this device is consuming work and we don't have actually any losses? The process is reversible. So this work should be maximum or minimum?
Minimum.
It should be minimum in this case because the system is consuming work in this case. And this is the difference. So in case of compressor, in this case, let's consider first of all a compressor. This is a compressor, symbol for a compressor. Usually compressor is used in air compression or gases. Flow is coming at low pressure, B1 under atmospheric condition most probably. and it is leaving actually at high pressure B2 is greater than B1. And this is the function of the compression, is to raise the pressure. And based on this, actually, we have to apply some work actually on this air in order actually to raise its pressure through the impeller of this compressor. Okay. So if we get back again, draw the control volume, and then apply the first law of thermodynamics, Q dot minus work dot equal to M dot multiplied by H2 minus H1. It is the same. But if this compressor is adiabatic condition, so this heat transfer is 0. If we divide by M dot like what we have done, then the work will equal to, the specific work will equal to H1 minus H2. But actually the work to the compressor is input work. So it should have what? Should have negative or positive sign?
Negative.
Negative sign. So we should have negative sign here. So negative will be positive. So the specific work will equal to H2 minus H1. If this process is actual process, so the work actual is equal to H2 actual minus H1. If the process is isentropic, the isentropic work will equal to H2S, the isentropic exit condition, minus H1 in this case. But let's look at this representation on the Molière diagram, HS diagram. This is the pressure at the inlet to the compressor. This is the pressure B1, low pressure, and the flow is compressed to a high pressure in this case. Let's say this is the inlet point, this is point number 1. If the process is isentropic, then we should not have actually change of entropy. Then we'll be reaching point 2S, which is isentropic exit condition. And in this case, we have delta S is equal to 0, or S1 is the same as S2S. We don't have any kind of losses. And this difference in enthalpy here should give us indication about the value of the isentropic input work. This isentropic input work to the compressor should be about what? Should be minimum in this case, because the device is consuming work. But if this device has some losses in this case, then in this case I have to increase the input work in order to overcome those losses. And in this case, those losses will be converted to, will appear in terms of actually entropy generation within the system, and it will result actually in increase of the entropy in this case. So instead of leaving at point 2S, it will be leaving at point 2A, which is the actual exit condition. And in this case, we should have some difference in the entropy delta S due to the irreversibilities within the system. Type H1, a difference between H1 minus H2 actual should give us indication about what? About the actual work in this case. Or H2 actual minus H1 should give us indication about the actual work. And this one, H2S minus H1 should give us indication about the isentropic work. And in case of compressor, the isentropic efficiency of the compressor is the ratio between the isentropic work divided by the actual work. It is the reverse issue that in case of turbine, as it is producing work, so actual is less than isentropic. So the isentropic efficiency of a turbine is the ratio between the actual work here divided by the isentropic work. But in case of compressor, as it is consuming work, so in this case, the efficiency of the compressor should be the ratio between the isentropic divided by the actual work. Or it is equal to work isentropic, H2S, the isentropic exit condition minus H1 divided by H2 actual minus H. And this is how we define the isentropic efficiency for the compressor in this case. Okay, so for the compressor, it is the ratio between the isentropic divided by the actual, because the isentropic work represents actually the minimum work in this case. We have another efficiency which is called the isothermal efficiency. But yeah, this is not required even for this course. But the isothermal efficiency is the ratio between what? The isothermal work divided by the actual work, not the isentropic. If you recall last time I told you that the isothermal process, if the process is isothermal here, it should result in the minimum compressor work. And it is lower than the case when it is isentropic. Okay, so the isentropic efficiency of the turbine is the isentropic work, which should be the minimum as it is reversible, divided by the actual work. There is another efficiency which is called the isothermal efficiency, which is the ratio between what? Not the isentropic work, because the isentropic work is not the minimum. The minimum work is for the isothermal work, which is equal to RT ln B2 over B1. Okay, so it is equal to the isentropic, is isothermal efficiency, which is here. This term here is the isothermal work divided by the actual work. But this is for your knowledge, okay? We are talking here only, we are limited in this course to the isentropic efficiency, okay? So what about if we have bump? Bump, it is the same concept like compressor. Its function is to raise the pressure, but compressor is dealing with gases and the bump is dealing with liquids in this case. So what is the difference? Liquid is what? Is incompressible. So in case of bump, in this case we are dealing actually with incompressible substance, or the density, which is 1 over a specific volume, is constant, or the specific volume is constant in this case. But if we have bump that is bumping a fluid isentropically or reversible. So if you look at the TdS relation, we have TdS is equal to delta H minus VdB. If the process is isentropic, so delta S is 0. So that means delta H is equal to what? Is equal to VdB. Delta H isentropic. Delta H isentropic, which is H2S minus H1, will equal to VdB. V is constant, so we just integrate here. So delta H will equal to H2S minus H1. For incompressible substance, volume is constant, so it will equal to V multiplied by B2 minus B1. So we can just replace this term, H2S minus H1, we can replace it by this term. In case of bumping incompressible fluid, which is the liquid case. So the isentropic efficiency for the bump, it is the same. H2S minus H1 like the compressor, divided by H2 actual minus H1. But in case of incompressible substance, for the case of bump, we can replace this term with delta H for the isentropic process to be equal to V multiplied by B2 minus B1, divided by H2 actual minus H1. Is that clear, Shabab?
Yes, clear.
So this is the isentropic efficiency for compressor and also for bump. Right, let's solve this example, and I will end up today. Okay. Type here in this example, he said we have air is compressed by an adiabatic compressor. So please, when you read the problem, just write down first of all the working fluid. If it is a steam, I will stick to the table or refrigerant. If it is gas, now I have decided in my mind that this is an ideal gas. BVRT is equal, can be applied in this case. So we have air is compressed inside an adiabatic compressor. So adiabatic heat transfer is equal to 0. And in this case, the device is compressor, which is open system steady flow device. Okay. The pressure B1 is given, is equal to 100 kilopascal at the inlet actually of this compressor. The flow is coming here at pressure B1 equal to 100 kilopascal and temperature is equal to 12 degrees C. Okay. He said this compressor is raising the pressure to 800 kilopascal, so B2 is 800 kilopascal, and the mass flow rate here, mass flow rate of air is equal to 0.2 kilogram per second. Okay, this compressor, as we said, is adiabatic, so don't have heat transfer. And he said the isentropic efficiency is given, so the isentropic efficiency of the compressor is equal to 80%. 80%, which is the isentropic efficiency should be 0.8 in this case. Okay. So he said we need to calculate the actual exit temperature. We need to calculate the temperature T2 actual, and also we need to calculate the power required, the shaft power input to this compressor. Okay. So whenever the isentropic efficiency is given or required, you have to start the solution with it. Okay. So the isentropic efficiency of the compressor is equal to H2S, the isentropic exit condition, or the isentropic work, H2S minus H1 divided by H2 actual minus H1. And see how we can proceed. Here, the working fluid is gas, and we said when we have gas, we have the constant, the specific heat approach, and we have the variable specific heat approach. Okay, you have to keep in mind this. In order to calculate delta H or delta S or anything for an ideal gas, we have two approaches. Here we have delta H, up and down, and it is gas. So in this problem, he didn't tell which approach you have to follow. So I will be following the variable specific heat approach. Solution using the tables in this case. So I will get H1, H2S, H1, H2 actual based on the values listed in the table. This is actually air, so tables from A17, let's recall this, to table A25. This is the variable specific heat. And in your exam, if there is a problem, I will just tell you which one to follow, constant or variable specific heat. But let's solve using the variable specific heat. So at temperature T1 is equal to 12 degrees C, you can go to table A17, then we can get the value of the enthalpy H1. Okay, for the process from 1 to 2. First of all, we don't have the actual exit temperature. So I need first to calculate this H2 actual. Then from table A17, at this temperature, we can have the value of enthalpy. If I have H2 actual, calculated it, then I can go to the table and then I can get the temperature T2 actual from the table. But I don't have the temperature, I have to solve for H2 actual. Now I have H1 at temperature T1. What about H2S, the process from 1 to the isentropic exit condition 2S. So we have S1 is equal to what, S2S, or the entropy is constant. Now we have an ideal gas undergo an isentropic process. If you recall this, we have also the two approaches, constant specific heat and the variable specific heat approach. Okay, in the constant specific heat, we said for delta S is equal to 0. In this case, given the pressure B1 and temperature T1, let's remind you with the slides. So here we said isentropic ideal gas undergo an isentropic process. Following the constant specific heat approach, we got this relation. So if I will be solving using the constant specific heat approach for this isentropic process, then I can say T2 over T1 will equal to B2 over B1 to the power K minus 1 over K. And the K for air is equal to 1.4. But I am not following this method now. This is the constant specific heat approach. We can use this equation. For the variable specific heat approach, we said delta S is equal to 0 for the isentropic process. In this case, given B1 and B2 and temperature T1. Okay, and I need to calculate the final temperature T2. So what should I do? At temperature T1, I will get H1, and I will get actually from the table A17, you will find here there is B relative and V relative in this table. So at the temperature T1, I can go to the table, get the value of H1, and get the value actually of B relative. Now at point number 2, B2S, which is the isentropic condition divided by B1, is B relative 2S divided by B relative 1. Okay, then we can say B relative 2S will equal to B2 divided by B1 multiplied by B relative 1. Then I can go to table A17. With this value of B relative, I can go actually and get actually the temperature T2S in this case directly. I don't need the temperature, just I need the enthalpy H2S. So and from table A17 with the value of B relative 2, I can go to table A17, then I can get the value of H2S in this case. So following the variable specific heat approach for an isentropic process, at temperature T1, I will get H1 and I will get B relative 1. Then I will be calculating B relative 2, which is at point 2S. This is applies only for the isentropic process. To get H2S, Okay. Now I have calculated B relative to S, which is this one, which is B2 over B1 multiplied by B relative 1. With this value of P relative from table A17, I can go directly and read the value of Insulby. Insulby in this case is H2S. Okay. Now I have H2S, H1, and I have the isentropic efficiency is equal to 0.8. Then I can calculate what I should have H2 actual. I have H2 actual, go to table A17, then I can get the actual exit temperature in this case. But what if I would be solving a Schwab using the constant specific heat analysis approach for the process, for the isentropic process from 1 to 2S? What should I do, Schwab, in this case? So instead of using table A17 and calculating B relative, I will be using directly this equation. So in this case, I can say T2S over T will equal to B2 over B1 to the power K minus 1 over K. K for air is equal to 1.4. Or you can check this value from table A to B. We have B2, B1, and T1. Then I will be calculating from this equation T2S. And in this case, I will change this term H2S minus H1 will equal to CB average, CB air, multiplied by T2S minus T1. I have calculated T2S, we have T1, and CB is calculated from table A to B at the temperature T1 in this case, because, or at the average temperature in this case, which is the average, which is T1 plus T2S divided by T1. Go to table A to B, get CB for air. CB for air is around 1.05 or something. Okay, then I can calculate this term. Take this term and substitute here directly, and also replace H2 actual minus H1 by CB average multiplied by T2 actual minus T2 actual minus T1. Even you can replace this CB with this CB and just take it as common. This is CB delta T, this is CB delta T. But as long as we don't have the actual exit temperature, we can assume we have the same CB value. So it will be the isentropic efficiency of the compressor will equal to T2S minus T1 divided by T2 actual minus T1. Okay. Then in this case, we can just get the value of T2 actual in this case. Okay. And T2S is calculated based on the isentropic relation. Is it clear, Shabab? I know,
Yes,
Yani,
yes.
maybe you are not following, but it's Yani, easy. If we have isentropic process from 1 to 2S, we have either constant specific heat, which is this approach. I can apply this relation to calculate T2S. Then calculate delta H is equal to CB delta T in this case. Or using table A17 with the temperature, you can go to the table and in this case get B relative 1 and then calculate B relative 2, and based on this we can calculate H2S. Anyway, you can substitute here, then we can get H2 actual, and the 17 we can get T2 actual in this case. Okay, so here is get back to our example. So here is this example. Now I have calculated T2 actual. We need to calculate the power input to the compressor. Power input, apply the first law of thermodynamics, like what we have learned in chapter 5. So work load of the compressor will equal to mass flow rate of air multiplied by H2 actual minus H1. We have calculated H2 actual, H1 mass flow rate of air is given 0.2. Then we can calculate this work in kilowatt. It will equal to 58, about 58 kilowatt.